Hi there, and welcome to the Villa Botcast, your on-the-go audio hub for smarter crop protection. Quick heads up before we jump in. This episode is voiced by AI for speed and accessibility, but every insight you hear was crafted by real experts at Villa. That means you get reliable, expert-backed information, anytime, anywhere.
Okay, let's jump right in. Today, we are taking a deep dive into a topic that's absolutely fundamental to crop protection. But it often, flies under the radar a bit. Spray adjuvants.
Right.
We've been digging into a stack of material and, well, it quickly becomes clear these products are far more than just additives.
Yeah, they're really crucial partners, and their performance is tied to things you might not even think about.
Especially, and this jumped out at me, the surprising complexity hidden in just plain water.
That's right. The sources are really clear. An adjuvant's job is basically to tweak the spray mixture itself, or to directly boost how well the main crop protection product, the CPP, actually works.
Like a wingman.
Exactly. A wingman for your active ingredients. That's a good way to put it.
So our mission for this deep dive is pretty straightforward.
Right.
Pull out the vital nuggets from this material for you.
Yeah, help you quickly grasp why these partners are so essential.
And how they're categorized, how they get used, and really zero in on those critical factors the sources highlight.
Like the water quality impact. It's huge.
It really is, because honestly, the water in your tank is, well, it's anything but simple.
It really isn't. The material we looked at goes deep into how specific dissolved elements in that water can actively work against your product.
Sabotage it almost.
Yeah, or if you manage it correctly, help it reach its full potential. It's all about understanding that kind of invisible chemistry happening before the spray even leaves the nozzle.
Okay, so let's get a clearer picture of these partners. The sources we have lay them out, organizing adjuvants into two main classes. This is specifically in the South African context mentioned in the material, right?
They do. You've got Class A, which are the efficacy-enhancing adjuvants,
Okay.
and then Class B, the utility adjuvants. And the difference is really about how they influence the CPP.
So Class A directly boosts performance, makes the main product work better.
Exactly. That includes things like surfactants, oil adjuvants, stickers, the stuff that helps it spread, stick, or get absorbed. And because they directly impact the CPP's punch, the sources say they have a tougher registration process. They're the performance enhancers.
Got it. They make the active ingredient better. So what about Class B then?
Class B adjuvants are more about helping the application process run smoothly or managing issues within the spray tank itself.
So their influence is more indirect.
Indirect, yeah. It's a broader category: buffers, products that manage salts, deposition agents to help droplets land right.
Drift control, that kind of thing.
Yeah, and compatibility agents to keep things mixed, defoamers, dyes, even tank cleaners fall into Class B.
Okay.
And because their effect is indirect, the material notes they generally have a lower registration hurdle. They make this system work better rather than the active ingredient directly.
Okay, that makes sense. Class A powers up the active, Class B smooths the operation.
Yeah.
Now, how do these partners actually get into the mix? The sources talk about two main ways.
Right. You can have the adjuvant prepackaged right inside the CPP formulation.
Built in.
Yeah, built in. That's called in-can. Or you can add it yourself to the spray tank as a separate product. That's the tank mix approach.
In-can sounds pretty convenient. What's the upside there?
Well, the biggest advantage the source points to is control. The company registering the CPP has total control.
Yeah.
They make sure the exact right adjuvant is in there at the right ratio relative to the active ingredient.
Okay, but I sense a but coming.
Yep.
There's a catch.
There usually is. The disadvantage, which the material highlights, is that the adjuvant rate is tied directly to the CPP rate.
Which is usually applied based on area, like acres or hectares.
Exactly. But what if the best adjuvant rate should actually be based on the total spray volume? Like a percentage.
Then you could end up with a mismatch.
Right. You might have the wrong adjuvant concentration for the amount of water you're actually using.
Okay, that makes perfect sense. The ideal amount of adjuvant might depend more on the water volume or conditions, not just how much active ingredient you're putting down per acre.
Precisely.
So tank mix gives you more flexibility.
That's the main advantage. With tank mix, you gain flexibility. You can adjust both the type and the rate of the adjuvant.
Tailor it.
Yeah, tailor it based on specific field conditions. Maybe the plants are really dense or big, or even the specific formulation of the CPP you happen to be using. You fit the partner to the specific job.
But what's the downside? When the user gets that control, there must be one.
Oh, yeah. The big drawback, and the sources really hammered this home, is that the CPP manufacturer loses control over what the end user actually does. So this often leads to people just skipping the recommended adjuvant, or maybe swapping it out for something cheaper or something totally unrelated or inappropriate.
And the material is pretty clear. This isn't just a minor oopsie. Skipping or messing up the adjuvant can cause real problems.
Absolutely. The consequences can be pretty severe. You might see the product simply not work as it should. That's inefficacy.
Right.
Or you might even get crop damage. Or physical problems like stuff precipitating out or turning into gel in the spray tank.
Ugh. Which, frustratingly, probably means you have to go back and reapply, right?
Yeah.
Costing time, costing money.
Exactly. The sources really emphasize that adjuvants are crucial for unleashing the full power of many CPPs, especially when conditions aren't, perfect.
So using them correctly when they're recommended isn't really optional?
No, it's essential for success, according to this material.
Okay. So we know what they are, roughly how they get mixed in. Now let's look at where they actually do their critical work. The sources have a really helpful way of thinking about this, breaking it down into 3 key places.
Yeah, it's like following the journey of a single spray droplet. The first place adjuvants are critical is right there in the water, in the spray tank itself.
Okay, so the liquid environment where the CPP is dissolved or suspended before it even gets sprayed.
Right, and this phase lasts from the moment you add the CPP to the water right up until that droplet finally dries on the target leaf surface.
And what's the big challenge in the tank?
Well, the material highlights a major battleground here. Dissolved cations. Those are positively charged ions, like minerals, basically.
Lurking in the water.
Lurking in the carrier water, exactly. And they can actively antagonize, sabotage, like you said, the effectiveness of many herbicides.
So the water itself can contain these hidden enemies.
It absolutely can. And pH is another factor in the tank. High pH levels, for example, can speed up the breakdown of certain insecticides.
Oh, wow.
Yeah, and it affects how soluble some herbicides are. So by managing the water quality with the right adjuvant,
You're winning the battle in the tank.
you're helping stabilize the CPP, making sure it's ready to work before it even leaves the nozzle, winning the battle in the tank. I like that.
It's fascinating. The water isn't just a passive carrier. It's this active chemical soup. Okay, so that's place number 1. Where's the second stop on this droplet's journey?
The second place is when the spray droplet is actually in the air.
Flying from the nozzle to the target.
That's the one, the journey through the atmosphere.
Sounds treacherous.
It can be. Out there, the droplet is exposed to wind, right, which can cause drift away from where you want it to go, and low humidity, which leads to rapid evaporation. Especially with the smaller droplets, they just disappear.
Meaning less of your expensive active ingredient actually makes it onto the plant surface?
Correct. So adjuvants help here too. They can help manage depositions, getting more droplets accurately onto the target. They can minimize spray drift from wind.
And slow down that evaporation.
And reduce that rapid evaporation, yeah. It's all about making sure the droplet survives its airborne trip and actually lands where it's supposed to.
Okay, tank, air. What's the third place?
The third place is that critical moment the droplet lands on the target surface. Usually that's a leaf.
The landing zone. What challenges does the droplet face once it finally gets there?
Well, for the CPP to actually work on the leaf, a few things need to happen pretty fast. There's retention. The droplet needs to stick and not just bounce off.
Right, like off a waxy leaf.
Exactly. Then there's spreading. It needs to cover enough surface area to be effective.
Not just sit there as a tiny bead.
Right. And finally, absorption. If it's a systemic product, the active ingredient needs to actually get into the leaf tissue.
And adjuvants help with all 3 of those stages on the leaf surface. Retention, spreading, absorption.
They do. They assist with managing retention, enhancing spreading, and boosting absorption.
When you're working with water-sensitive herbicides, every detail counts. That's where Class Act NG comes in, a 4-in-1 adjuvant that gets the job done. It neutralizes salt antagonism with ammonium sulfate, enhances uptake with corn sorb technology, spreads evenly, and reduces foaming, all in one pass. More absorption, more impact. Class Act NG, the smart choice for tough tank mixes.
The sources actually offer a pretty simple way to think about the overall role of adjuvants across all 3 stages.
Oh, yeah.
Yeah. In the water, in the air, and on the leaf, They fundamentally help get more active ingredient onto and into the target.
So it's framed as sort of a numbers game.
Exactly.
Yeah.
And adjuvants are the tools that stack the odds in your favor at each critical step.
That really clarifies it. Maximize the potential by surviving the tank, surviving the air, and conquering the leaf.
Okay, let's circle back to that first place, the water, because the sources put a huge emphasis on this. They basically say if you even suspect your water source might be antagonistic.
Get it tested.
Yeah, water analysis isn't just a good idea, it's, quote, necessary. Necessary is the word they use. And the sources explain why. The advantages are huge. A water analysis lets you maybe pick a better water source if you have options.
Right.
And crucially, it lets you figure out the correct type and rate of adjuvant you need to counteract whatever problems you find in that water.
So it's really a foundational step for effective crop protection, not just something you do if you think there's a problem.
Exactly. It takes the guesswork out. The material even mentions that for common water conditioners like ammonium sulfate AMS or certain buffers, there are detailed rate selection charts and calculation methods available.
All based on the water test results.
All based on the analysis.
That precision must save a lot of headaches. And probably money, too.
It absolutely does. Applying the correct adjuvant rate stops you from underdosing where it doesn't work or overdosing, which is wasteful and potentially harmful.
Makes sense.
The sources even give practical tips for getting a good water sample, like rinse the bottle first with the water you're testing.
Oh, good tip.
Yeah, avoid soap, fill the bottle completely so there's minimal air, store it away from contaminants, and ideally keep it cool and dark, maybe in the fridge.
Good common sense advice to make sure the test is actually accurate. What kind of analysis is usually needed? Is it super complex?
Well, the sources suggest that often a simple test just for electrical conductivity, EC and pH, can give you a pretty good read on suitability.
Okay, EC and pH and EC measures.
EC is basically a measure of the total dissolved salts in the water. So high EC generally means more dissolved ions floating around.
Got it. So EC and pH are like the quick check.
Right. But if there's any doubt at all about the water quality, a full water analysis is highly recommended. The sources point out that many labs can do this specialized analysis.
Okay, let's dive into those specific problem ions that a full analysis would uncover. Which ones are the main culprits, according to this material? The big troublemakers.
The sources call out several usual suspects. Calcium and magnesium are primary concerns.
Hard water, basically.
Yeah, water high in those is often called hard water. And the material clarifies something interesting. While hardness technically refers to how well soap lathers.
Right.
In the context of CPPs, hardness really just signals antagonism. It doesn't matter if it's temporary or permanent hardness. Both are bad news for certain products.
And hard water, so calcium and magnesium, actively antagonizes a whole range of common herbicides.
Yes, the material specifically lists glyphosate, glufosinate, and several of those water-soluble phenoxies like 2004-diamine, dicamba, and MCPA. Big ones.
Okay, what about sodium?
Sodium's another one. Sodium-rich water is often called brackish, maybe tastes a bit salty if chloride is present. But sometimes sodium is linked to bicarbonate instead. Sodium also antagonizes a broad spectrum of herbicides, includes the ones we just mentioned like glyphosate and glufosinate,
Okay.
plus certain sulfonylurias, and some from the cyclohexanedione family like clethodim and cycloxidum.
Wow, that's quite a list of really common chemistries affected just by calcium, magnesium, and sodium. Any others? What about potassium?
Potassium is also noted as antagonistic, but the sources say it's typically found at lower concentrations than calcium, magnesium, or sodium.
So less of a problem than usual.
Usually. Its antagonistic power is also a bit less, but the material does warn that in rare cases with extremely high potassium levels, the potential for problems is still significant.
Okay. Any other major ions on the list that are particularly nasty?
Iron. Iron is highlighted as a heavy metal.
Wow.
And while it's not usually present in huge amounts, the sources describe it as an extremely antagonistic occasion. The word they use is it can devastate the activity of many herbicides.
Devastate. Wow.
Yeah, and here's a really critical point. Common adjuvants like ammonium sulfate, AMS, which work pretty well against calcium, magnesium, and sodium.
They don't work as well on iron.
They're less effective at overcoming iron antagonism. So the recommendation, if you find high iron, is basically if you can possibly avoid using that water source, do it.
Wow. Okay. Devastate is a strong warning. It really shows how potent some of these dissolved things can be. So we've talked of gations, the positive ions. What about the negative ones, the anions?
Bicarbonate. Bicarbonate is singled out as by far the most important anion you'll frequently run into at problematic concentrations.
Okay.
Carbonate has similar properties, but it's usually only present if the water pH is really high. So bicarbonate is the main one.
And bicarbonate and carbonate, they're responsible for something called buffering capacity. Is that right?
Exactly. They contribute significantly to the water's buffering capacity, which is very closely linked to alkalinity.
Buffering capacity is.
It's the water's ability to resist changes in pH when you add something acidic or basic, like, say, a crop protection product or maybe a specific pH-adjusting adjuvant.
Ah, I see.
And the sources note this gets kind of complex because it's tricky to fully separate the antagonism that's caused by the bicarbonate ion itself from the antagonism caused by the pH level that often goes along with high bicarbonate.
And this sounds like where that really interesting idea of masked antagonism comes into play.
It does. The sources give a great example using certain sulfonylurea herbicides.
Okay.
Sodium bicarbonate in the water can antagonize them. It's actively working against the herbicide. Okay.
Right. Bad news.
But at the same time, the higher pH level that often comes along with sodium bicarbonate actually increases that same herbicide solubility and activity.
So, wait. The bad effect of the salt antagonism might be completely hidden or masked by the good effect of the higher pH.
That's precisely what the sources call masked antagonism. You could use this water source, apply the product, see pretty good results.
And think the water's fine.
Exactly. Assume the water's fine because the antagonism is just hidden by that boosting effect from the high pH.
But then
Maybe you switch to a different water source, one that doesn't have the high pH, but it still has other antagonistic ions, maybe calcium or something. And suddenly, the same herbicide might fail or not work nearly as well, because now the antagonism isn't being masked by the helpful high pH anymore.
that is a truly critical insight. You could be getting like adequate results in one situation, thinking everything's okay, when there was an underlying issue there the whole time, just concealed by another factor in the water.
And the material makes it really clear. Understanding your water quality, doing that analysis, and then using the correct adjuvant technology can help eliminate this masked antagonism,
Leading to more consistent, more reliable product performance across different situations.
Exactly.
Wow. This deep dive has really opened my eyes to that hidden world inside the spray tank and in the air, and just how vital these adjuvant partners really are.
It's a complex system, isn't it? And understanding it is definitely key. We've covered a lot of ground.
Yeah.
We looked at what adjuvants are, those Class A and B classifications, and how that affects registration.
Right, the performance enhancers versus the system smoothers.
Yeah, and the trade-offs between putting it in the can versus adding it in the tank.
The control versus flexibility dilemma.
Exactly. And we followed that droplet's journey, seeing where adjuvants lend that crucial support in the water, through the air, and finally on the target leaf surface.
And we spent a good chunk of time on that foundational step the sources kept stressing.
Yeah.
Managing the carrier water.
Mm-hmm.
We saw how getting a water analysis really moves beyond just being a good idea to being, well, necessary, like we said.
Necessary for picking the right adjuvant, the right rate.
Which directly translates to better efficacy, avoiding those costly mistakes like having to respray or, worse, damaging the crop.
Absolutely. And we highlighted the surprising power of those dissolved ions, calcium, magnesium, sodium.
And especially iron. That devastate warning really stuck with me.
Yeah, actively working against your herbicides. And we touched on bicarbonate, adding that extra layer of complexity with buffering capacity and pH interactions.
You know, being better informed about these details directly from the source material we looked at, it really feels like it gives you a shortcut.
A shortcut.
Yeah, a shortcut to avoiding those common pitfalls they described, using the wrong adjuvant or none at all, and wondering why things aren't working.
That makes sense. And that concept of masked antagonism is such a powerful takeaway, I think.
It really is.
The way the sources show how one factor, like that higher pH, can completely hide the negative impact of another, like the salt antagonism.
Making you think a product is working fine.
When an underlying issue is just sitting there waiting to cause a failure in a different scenario.
It definitely leaves you with a thought that goes beyond just the spray tank, doesn't it?
How so?
Well, it makes you wonder, how many other complex systems do we interact with every day where multiple factors are playing out?
Ah, I see where you're going.
And some of those factors might be masking underlying problems that we just don't see. It's
Yeah.
kind of a reminder that really understanding the hidden dynamics, digging a bit deeper, is often key.
That's a great thought to end on. Looking for the masked issues everywhere.
Thanks for listening to the Villa Botcast, powered by AI, driven by insight.